Today we are going to enter the third part of this chapter. So today you have to learn how to identify and draw subgraphs and tree. So what is a subgraph? So subgraph, just a part of a graph or the whole graph redrawn. This is drawn again, okay? Just a part of the graph or all the graph redrawn without changing the original positions of the vertices and edges. So graph H is a subgraph of G. So why graph H is a subgraph of G means that why it is a part of the graph of G or it is a whole graph of G. If all the vertices in the graph H is a subset of the vertices in the graph G, or all the edges in the graph H is a subset of the edges in the graph G, and the vertex pair of the edges of graph H are the same as the edges of graph G. And now we determine whether diagram 1, diagram 2, diagram 3, and diagram 4 are the subgraph of graph G. Where is graph G? So here is a graph G, and we see that if all these diagram 1, 2, 3, 4 are the subgraph of G. So still remember, the subgraph means a part of the graph. Is it a part of the graph, or is it the whole graph of the graph? So make sure that the position of the vertices must be the same and the position of the edges must be the same. Now we look at the solution. So diagram 1 is a subgraph. Okay, what is the subgraph of graph G? Is it a part? You can see that the positions P, S are the same and it is joined by the E5, and we can compare with graph G where PS is joined by E5, so the position is not changed. So yes, it's a subgraph because the vertex pair, okay, the vertex pair for HE5, the vertex pair of pair E5, HE5 is PS, it's the same. Now we go to diagram 2. Are all the positions same as the graph G? No, because the position of loop E2, you see that? The position of loop E2 is not on vertex Q, so original the graph G, the E2 is supposed to be a Q, but diagram 2, the E2 is a P, so it's not a subgraph. Then we go to diagram 3. So diagram 3, okay, did they have the same positions? So Q, they have a loop E2, yes, it's E2, but you can see that for the pair, the vertex pair PS is connected by E3, but if you compare with graph G, PS is supposed to be E5, so no, it's not a subgraph. So because the edge connecting vertex P and vertex S is not E5, where it is supposed to be E5. Then we go to diagram 4. You compare again. So seems like there is some problems because E4, the loop Q is E3, and suppose the loop should be E2, so it is not the subgraph because the loop and the edge connecting Q and R. Okay, Q and R here is E2, but here is E3, so they are wrong. So just now it's a subgraph and now it's 3. So what is 3 actually? 3 is a subgraph also of a graph, but with the following properties. Okay, so keep in mind that 3 also a subgraph, but there is some properties of 3. 3 is a simple graph, so without loops and multiple edges. So just now the subgraph can be loops and multiple edges, but for 3, where it is a subgraph also, cannot have a loops and multiple edges, where all the vertices are connected. all the vertices must be connected. You cannot have an isolated vertex. And each pair of vertices is connected by only one edge, so you cannot have a multiple edge. Each pair of vertices must only connect by one edge only. And how do you calculate the number of edges? There is a number of vertices minus 1 for the subgraph of this tree. For example, if number of vertices is n, then the number of edges must be n minus 1. It's like this. For example, the number of vertices, for example, you have 5 vertices, and for a tree, the number of edges must be 4. Or the number of vertices is 10, and the edges must be 9. So this diagram is a tree. So why is a tree? Because all the vertices are connected. You can see the A, B, C, D, E is connected. No vertex is alone. And there are no loops or multiple edges also. It's simple. Every pair of vertices is connected by an edge. So you can see that this pair is connected by one edge. So this pair connected by an edge. So this pair connected by an edge. And this pair connected by one edge only. There are 1, 2, 3, 4, 5 edges. 1, 2, 3, 4, 5 vertices. So 5 vertices must have 4 edges for 3. 5 minus 1 equal to 4. So is this a tree? This is not a tree. So why? Because vertex B and vertex E can be connected in two ways. So B can directly go to E, and B can pass through C, pass through D, and go to E. So this is not a tree. And you have 5 vertices and 5 edges also. So this is not a tree. Remember, a pair of the vertices must have an edge and only be connected in one way. And since B and E can connect in two ways, so this is not a tree. For this example, we try to determine whether each of these following graph is a tree or not. Then justify your answer. So we look at the first one. So this is not a tree. Why? Because you got 6 vertices and you have 7 edges. So each pair of vertices can be connected in various ways. You see that if P go to Q, another way is from P pass through U, T, and then go to Q. And P also can pass through U, T, S, R, and go to Q. So you got various ways. So this is not a tree. And then B. B is a tree because for a tree you got n minus 1 edges. So you have 6 vertices and you got 5 edges. And each pair of vertices is connected by one edge only. Then we go to C. C is also a tree. You got 6 vertices and 5 edges. Okay, if you calculate, and each pair of vertices is connected by one edge only. And D is not a tree because you have 6 vertices and 4 edges, and vertex R and T are not connected to the other vertices. They must be all connected, and R and T here are not connected. Then how about to draw a tree? So according to this information, you got 8 vertices. So 8 vertices must have 7 edges. Then you draw 8 vertices. 1, 2, 3, 4, 5, 6, 7, 8 vertices and 7 edges. So you just draw like this. And you can also draw like this. You see that? You have 8 vertices and 7 edges. If 4 edges given to you, it means that you got 5 vertices. So you can draw 1, 2, 3, 4, 5. and then all the edges you just join in. You got many ways to draw. You either draw like this or the example just now. Now for this example, you try to draw 2 trees based on the graph given. So remember, to draw the trees, all the vertices must be connected and also must be in the same positions. So you have 5 vertices here, so of course you must have 4 edges for the tree. So you can draw like this, 5 vertices and 4 edges. So you have edges here, here, this part and this part. So you got 1, 2, 3, 4 edges. Another one, you can draw like this. Remember, the positions must be the same. This part, this part, this part, and all the vertices are joined, so it is bisected. Now we go to these examples. Also draw 2 trees. So you have 1, 2, 3, 4, 5, 6 vertices. So the tree that you draw must have 5 edges. So you draw all the vertices first, and then you try to draw the edges. So you can draw here where all are linked. Okay. Another one is like this. So based on your creativity, but make sure that all the vertices must be linked. So this gives you 6 vertices and 5 edges. Where if you compare with the original graph, actually here you got 8 edges and exit 3. It's okay, as long as all the vertices are connected and with 1 edges for each pair of vertices. So how to solve these problems? So this diagram shows an undirected weighted graph, and you try to draw a tree with a minimum total weight. So here you have a rate, 25, 20, 10, 12, 19, 14, 17. Here are all the weights. So the solution here, the original graph got 5 vertices and 7 edges, but if you want to draw a tree, you must have originally have 5 vertices. You must have 5 vertices, but you must have 4 edges. So what you need to do is you have to remove 3 edges. So if you want to have a tree with a minimum total weight, so we have to remove the edges with the greatest weight. Where are the edges with the greatest weight? 20, 25, and 19. So 20 we remove 25 and 19. So actually we can get a minimum total weight, but this is not a tree. Okay, so we cannot accept this. So since just now it's not a tree, so we go another step. We go to step 2. So we remove 20, also the greatest weight, part of the greatest weight. Then we remove between 19 and 25. So we try to keep 19 because the weight is smaller, so remove 25. So what we need to do next? So between 12, 14, and 17, we remove 17. So this is a tree because all vertices are connected, and the minimum total weight of this tree is 55. So we add out 10, 12, 19, and 14, so we'll give you 55. Now you can try to complete the self-practice 5.1c, page 142 for question 1 to question 6. That's all for today and for this part of the topic.